Hello, in this video we will look at CPU context switching. We will see how the operating system enables multiple processors, or rather enables multiple processes to share a single CPU. So, let us consider this particular figure where we have a single CPU in the system which is shared among multiple processes. So, the operating system by a feature known as multitasking enables that this CPU is fairly shared among the various processes. So, in a multitasking environment, or rather in a multitasking enabled operating system, the OS would allow one process to execute for some time, and then there is a context switch. So, during this context switch, the process 1 would be stopped and a new process, in this case process 2, will begin to execute. Now, the operating system ensures that when process 1 stops executing, its state is saved in such a way that after some time it can be scheduled back into the CPU and can continue executing from where it had stopped. So, as a result, in a multitasking environment such as this, processes execute for brief intervals of time known as time slices. So, for instance, process 4 executes in this time slice, then there is a period where it does not execute, and then it continues executing in this time slice, and so on. So, in this video what we are going to see is how the operating system ensures that a context switch occurs. To begin with, we will see what triggers a context switch in an operating system. To answer this particular question, we need to go back to the process state diagram. So, in a previous video on the processes, we had seen that when a process gets created to the time it exits, it goes through several different states, and this is represented by this process state diagram. What we will see now is how these various states will trigger a context switch to occur. Let us see this first scenario about how a context switch gets triggered. Let us consider this particular program which essentially invokes the scanf. Therefore, it requires a user to input something through the keyboard. Let us say this function is executing as a process in the system, and it is currently in the running state, which means that it is currently holding the CPU and is currently executing in the CPU. When the scanf function gets invoked, what would happen is that the process now requires to be blocked until a user inputs data through the keyboard. So, as a result, the state of the process changes from the running state into the block state. Now, the process will remain in the block state until the user has input data into the console. So, in order to utilize time effectively, what the operating system is going to do is that it is going to trigger context switch, so that an other process could then be executing in the running state and will have the processor. So, let us take the second scenario where context switch can occur. So, let us say that we are considering this particular program where there is a printf and then there is an exit, and as we know and we have seen before in a previous video that the exit is a system call which results in the process going into this zombie state. So, at the end of the exit system call, the operating system will trigger a context switch. So, this will ensure that the current process which is just in an exiting mode will not have the CPU resources anymore, but rather a new process will be assigned the CPU. Therefore, a new process will come from the ready state into the running state. Now, let us look at the third scenario that can occur. So, if a process is in a running state and an event such as an hardware interrupt occurs, then it could lead to a context switch. So, for instance, if a process is currently executing or currently holding the CPU and an interrupt occurs, it moves from the running state into the ready state. As a result of the interrupt, it would cause an interrupt handler to execute, and at the end of the handler a new process may be executed in the CPU. That is, a new process will move from the ready state into the running state. A very popular interrupt in this context is the timer interrupt. Now, all systems have a timer within them. So, this timer is configured to send interrupts periodically to the CPU. The period could be anything from 10 milliseconds to 100 milliseconds and may vary from system to system. Or when the timer interrupt occurs, the OS gets triggered and it causes a CPU scheduler to execute. Now, the CPU scheduler looks at the queue of processes which are in the ready state, and then based on some algorithm will choose a particular process. So, this process would then be moved from the ready state into the running state, and it would be this process that would execute in the CPU until the next interrupt that occurs. So, in this process every 100 milliseconds, for instance, the scheduler would pick a new process to execute, and that process would then hold the CPU for the time slice of 100 milliseconds. So, now let us look more into detail about how a context switch occurs. So, in a previous video we had seen that corresponding to each process in the system, the kernel stores some metadata. Essentially there are 3 metadata for each process. They are the process control block, the kernel stack, and the page tables corresponding to that process. Now, we have also seen in an earlier video that when an interrupt occurs, this context of that process is stored in the kernel stack in what is known as the trap frame. So, this context would allow the process to restart execution from where it had stopped. So, in this particular figure, for instance, each process has its own trap frame or own kernel stack which stores the trap frame when an interrupt occurs, and its associated page tables. Similarly, process 3 has its own trap frame and page tables, process 1 and process 2 as well. In addition to this, the CPU scheduler has a context which is also stored in a separate stack. So, this is known as the scheduler context, and it is used while doing a context switch. So, let us look more into detail about how a context switch occurs. Let us assume that the user process 3 is currently executing in the CPU, that is, the user process 3 currently holds the CPU. Also, as a result of this, it is the process 3's page table which is currently active, that is, for every instruction fetch, every memory load or memory store, it is the process 3's page table which does the translation from the logical address into the physical address. Now, when an interrupt occurs, we have seen that there is a switch from the user mode into the kernel mode. Therefore, the kernel begins to execute again, and it is the kernel which will now hold the CPU. All instructions that are being executed in the CPU thus belong to the kernel code. Also, as a result of the interrupt, what we have seen before was that the entire context of this process 3 gets stored in the kernel stack of that process. This context is stored in a structure known as the trap frame, and this trap frame, as we have seen before, has sufficient amount of information that would allow process 3 to restart executing from where it had stopped. The next thing that happens is that the kernel determines that the interrupt occurred was due to the timer, and it would invoke the scheduler. The scheduler would then switch from the kernel stack of the user process to its own stack or the scheduler stack. Therefore, it would obtain the scheduler context. The scheduler then chooses from the ready list the next process to be executed in the CPU, and then there is a switch to the new process's kernel context. Thus, we are moving back from the scheduler's context back to the new process, in this case process 4 that has been selected by the scheduler, and we switch back to process 4's page tables and process 4's kernel stack. Now, recall that each of these stacks have the trap frame. Therefore, even process 4 based on its previous execution has a trap frame which contains the entire context of where process 4 had stopped executing. Thus, when the timer interrupt returns with the iret call, this contents of the process 4's trap frame gets restored, and as a result of this process 4 will continue to execute. Also what happens is that we are switching to process 4's page table. Now, as process 4 executes instructions, its instructions are fetched, memory loads and memory stores are translated by process 4's page tables. In this way, every interrupt that occurs would cause a switch to the kernel, and if it is a timer interrupt and requires a new process to be executing, the new process would be selected by the scheduler and its context would be restored. Also, as we have seen, the new process's page table would then be made active. Now, let us look how timers actually interrupt processors. As we have mentioned before, all systems have a timer present in them. In legacy systems, this is known as the PIT, or programmable interval timer, which is a dedicated chip present in the motherboard. In modern systems or in current day systems, timers are present in the LAPIC. So, in both these devices, there is a counter present internally. So, this counter can be programmed to start counting from a particular number, for example, this large number. Every clock cycle, this counter is actually decremented until it reaches 0. At the end of the count, that is when it reaches 0, the counter is loaded back with the original value and this process continues. So, essentially the counter keeps going from this large value to 0 and then keep cycling across these values. Now, when 0 is obtained by the counter, an interrupt is asserted to the CPU. Thus, at periodic intervals, the CPU would receive interrupts from the timers. So, these interrupts are then used to decide on the next process that is going to execute in the CPU. This figure over here depicts the ideal view of multitasking. So, in this particular ideal view, a process will continue to execute until its time slice completes. When its time slice completes, a new process or another process will execute in the CPU. In a more realistic view of multitasking, and also as we can infer from the previous slides, is depicted in this particular figure at the bottom. So, in this view, the more realistic view, the process will continue to execute as usual until its time slice completes, and then instead of the next process immediately being context switched into the CPU, the kernel will execute, wherein the kernel will do various things like handling the interrupts, doing the various jobs, and also executing the scheduler where a new process is chosen, and only after this all this occurs will this next process execute in the CPU. So, this time difference between when the first process is preempted from the CPU to when the second process starts to execute is the context switch overheads. Now, this context switch overheads could be significant. The factors affecting the context switching overheads can be classified as either the direct factors or the indirect factors. Among the direct factors, these are the 3 examples of direct factors, and they are essentially quite straightforward and easy to understand. For instance, the timer interrupt latency, or for that matter any interrupt latency, will add up to overheads in the context switching. Essentially, there would be time taken for saving and restoring context for the various processes. In addition to this, overheads are also caused by the scheduler which needs to choose the next process to execute in the CPU. The indirect factors are more subtle and more difficult to understand. So, these are 3 examples of indirect factors. So, the first factor is the that the TLB needs to be reloaded. So, TLB is the translational look aside buffer. So, it is a cache which stores recently used page mappings. So, when we switch from one process to another process, we know that the page table change from the earlier process to the new process, that is we have a new set of page tables which becomes active. As a result, the TLB needs to be flushed again. Now, refilling the TLB will take time and result in overheads. So, another aspect is the loss in the cache locality. So, as we know, cache memories work on the principle of locality. So, when there is a context switch, this locality is lost, in the sense that we are no longer executing the same instructions as we had done before the context switch. So, as a result of this, the cache memories would need to be reloaded again, and this could incur several cache misses and as a result add up to overheads. Another aspect is that every time an interrupt occurs, the processor pipeline would need to be flushed. So, this also adds up to the overhead. The context switching could incur significant overheads and degrade performance quite significantly. As a result, designers should very carefully decide upon how context switching is done, and rather when it is done, in order to achieve best performance of their system. With this, we will end this particular video on context switching in operating systems. So, we have seen various aspects of context switching. Essentially, we have seen some details about how context switching occurs in operating systems, and we have also seen overheads that are incurred due to context switching. Thank you.